Okay, so just very, very quickly, Thor already covered, so I'm Claudia Filippi from the University of Twente in the Netherlands, and this is the team who will be engaged in helping you also when we go to the practical session. And then there is Anthony Semama, who will give you lectures also on Monday and Tuesday from CNRS in Toulouse. Okay, so all of us are part of TREX, that was mentioned a few times. That TREX stands for Targeting Real Chemical Accuracy at the Exascale, and is a so-called Center of Excellence in Exascale Computing. So the European Commission has been investing in building these big computers, but at the same time has also been investing in making sure that some software will actually run on this computer. Okay, and so essentially, the effort has been to bring different communities, from I don't know, from fluid simulation to indeed quantum mechanical simulation, to this new architecture. Okay, so and we are in particular focused on high accuracy quantum chemistry, mainly stochastic. So we develop, we modernize, we upgrade. We are developing codes in QNC, and also some few selected more, let's say, standard quantum chemical codes. And today we focus on two. One of them is quantum package, indeed mainly developed in Toulouse. So Anthony is the expert, and that's a very special quantum chemistry code for doing selected configuration interaction calculations, and also mix wave function and DFT type of approaches. And on our side, we are having CHAMP, which is a quantum Monte Carlo code. Okay, and the two codes are talking to each other, also via some I/O library developed within TREX, and the idea is also to speed up QNC using some libraries which we are developing within TREX, and which will also be adapted to the new architectures. So okay, so I see there is already a question in the chat, but I will go for a little while unless it's very urgent. And yeah, okay, very good. And then maybe I stop at some point to ask if there are very urgent questions. Okay, I will start. I understand that some of you really know nothing about quantum Monte Carlo. It's really a first encounter. So I will go a bit slow at the beginning. Okay, so with the name Monte Carlo, we are denoting a wide class of approaches which make repeated use of random numbers. Okay, and you can do so to actually really simulate a stochastic events, but like in our case, you can also employ random numbers to solve a deterministic problem. Okay, so some of you, if you are a physicist or a chemist, you might have encountered this method in statistical mechanics. Okay, because they are used to sample, so to get configuration in whatever space you are, so sample the Boltzmann distribution, and therefore compute averages, so thermal averages, which are integrals in many dimensions. Okay, and once you go from classical to quantum simulation, you add a quantum in front of the Monte Carlo, you have quantum Monte Carlo methods. Now, the simple example, if you're doing some Googling of a Monte Carlo simulation, essentially is to use random number to compute pi. Okay, to compute starting from the area of a circle. Okay, so you're taking your circle, you are inscribing it in a square, and now you're starting to throw some darts. Okay, we are assuming you're really a very bad player. Okay, so you're gonna throw them randomly, but you're still gonna hit the square. Okay, and then what you do is at the end of the day, you have thrown so many darts, and you're gonna count how many are inside the circle. So that's red with respect to the total number, red and blue. Okay, so in the ratio, if you take the ratio, so this is not really an equal, it's an estimate. If you're really doing many, many hits, you will get, that this is proportional, so this is equal to the ratio of the areas of the circle divided the total area of the square. Okay, and that's a way to compute pi. Okay, so maybe not the most efficient, but that's a way to compute pi. So now let's assume we want to do the integral of a function. You could say, well, I still do rejection method. You could say, well, this is my function. I will compute the integral. That's an area. I could still inscribe, this area in a rectangle and start to throw darts, but that's not the way we're going to do it. Okay, so the way is you say, well, I'm interested in this integral over the segment AB. What I do is I multiply by b minus a and I divide by b minus a, and then I focus on computing this part, okay? This average of the function f of x, over the range AB. So now we focus on this, so by just multiplying by b minus a, we recover the full integral. And now you can see that that's f of x, so that's my original function, multiplied by p of x. And p of x is simply this object, is 1 over b minus a over the segment AB. Okay, so this is a probability density, so it's positive. It integrates to 1. Okay, so the probability of getting, a number, if I use p of x, probability of getting a number in a segment is constant, is 1 over b minus a times the x. And what you can do, you can use a random number generator to get, points distributed uniformly in the segment. Okay, so you throw again all these points between a minus b uniformly, it's flat, there is no structure in this probability density. And then what you do is you're having the integral, so f of x, and you just accumulate it over the samples you have taken, and that's an estimate of your integral. Now, if you're having such a function instead, very peaked, so still, let's say, constrained in the segment AB, but, sorry. Too fast, still constrained in the segment AB, but let's say much more peaked, you don't want to just multiply by b minus a 1 over and divide by b minus a, so you don't want to sample points in a uniform distribution on the segment, but you would like actually to have something which resembles as much as possible the function you're interested in. So let's assume you are able to actually sample point according to p of x. You will multiply by p of x, divide by p of x, and then what you will do is you will start to throw configuration, to sample configuration, which will be, you will have many more close to the center and much fewer close to the edges. Okay, and now again by computing a lot of them, so you draw a lot of configuration, you sample a lot of configuration according to p of x, you can estimate the integral by summing whatever is this local quantity, f divided by p, over the configuration and divided by the total number of configuration. And that's an estimate of your integral. Now, okay, so now, so let's us think about the problem in a nutshell. So we are having an integral of a function, was called f, let's call it a, and you're taking its average with this probability distribution. Okay, so what we are taking probability density, we are taking p of x to b is greater than or equal than 0. It integrates to 1, and then we sample. We're going to have to see how we sample, how do we achieve such a sampling of configuration according to p of x. And we estimate then this integral, the average of a, as, let's say, by summing all the a over the sample divided by the total number of samples. Okay, and now in statistical physics, what you're having, that p of x is your Boltzmann distribution. Okay, so here is your energy of the configuration. So, very good, so you're saying, fine, I can compute integrals with a Boltzmann distribution, but, we are really here focusing on quantum mechanical simulation. Okay, so some of you might be very familiar with density functional theory, which is extremely powerful, can handle very large systems, but as you might know, it has an approximate component, the exchange correlation function, and often is there are a lot to choose from, and often you find the one which works for your system, but if you don't, you must do something else, okay? And the something else can be quantum chemical approaches, so you go beyond Hartree-Fock. They're accurate on a small to medium system. There are a lot of acronyms and flavors, and some of them are also being being pushed to larger and larger system to run on this type of architecture as the one discussed by Thor. Okay, and then there is us, Quantum Monte Carlo. So we are also handling a solution of the Schrödinger equation, but instead of just doing in a deterministic manner, we are using random numbers. So we do so stochastically. And if you look in the literature, you will find accurate, sometimes benchmark calculation for medium to large system. Okay, and I will qualify a bit better what I mean. Okay, so here, even for Quantum Monte Carlo, there are different ways of doing Quantum Monte Carlo. Okay, here what we will focus today is what we call a real space Quantum Monte Carlo. So the configuration we draw are actually the 3n spatial component of the electronic coordinates, if n is a number of electrons. Okay, so why doing QNC is the favorable scaling. So the energy will scale like order n to the fourth. So that's a nominal scaling. Of course, there is a prefactor. The nominal scaling of DFT is n cube. If you go to very high level couple cluster, you will go beyond n to the 6. Okay. A great advantage of the fact that we are using random number is that all integrals are computed not analytically, but in a stochastic manner, and so we're having a lot of flexibility in the choice of the wave function. The approaches are very easily parallelizable. And as I said, you will find, mostly calculation for first and second row, routinely up to 100 atoms. And this is already, 5 years ago, a calculation by Dario Alfé and collaborators on benchmarking van der Waals functionals on, pretty large complexes. This is a C136H44. And I will get back to this benchmark towards the end of the lecture of tomorrow. So now let us see Monte Carlo in practice for a quantum observable. Okay, so let's take the Hamiltonian. So let's assume we are interested in computing the energy. Then what you will do if you're given a wave function psi is to sandwich the Hamiltonian between the wave function and divide by the norm. Okay, so that's an integral. You have an integral in the numerator and in the denominator. Okay. Then what you try to do is to rewrite in terms of a probability density. So what we do is we multiply and divide by psi. Okay, so we end up with h psi over psi. We have psi square up here. And what we do is we bring the denominator, so the object downstairs, inside the blue box. Okay, so this quantity is our P of R. Okay, so R are the electronic coordinates. Okay, is our P of R is greater than 0, greater or equal than 0. They are fermions, greater than or equal than 0, and integrates to 1, and therefore I can interpret it as a probability density if I'm able actually to sample it. Okay, and what I will do therefore is this is my P of x, and the integral can be rewritten as this local function EL of R. We called it before f of R of a of f of x or a of x. So this is the local energy. And we write it as an average of the local energy over the samples drawn, distributed according to P. So the idea therefore would be that your sample sees 3n configuration from P, and we're going to do so using Metropolis algorithm. We come back, we get to it in a moment, and then we are averaging the local energy, over the configuration, and that gives us an estimate of the energy. Okay, so and to do so, we perform a random walk in this 3n dimension, where n is the number of electrons. Okay, so this is a trick to evaluate integrals in many dimensions, and can be pretty large. And the advantage indeed is that if you're doing so, you're not constrained, for instance, to use Gaussian as a representation of your orbital. You can also put, Rij terms, so interelectronic distances inside your wave function, and you can compute your integrals with Quantum Monte Carlo. Okay, so now let's see, this trick is important because, as I said, the dimensions are many. So if I take a very small cluster, a silicon-21H22, let's assume I throw away the core electron, so I end up with 4 valence electrons per atom. I still have a total of 106 electrons. If I multiply by 3, which is the number of dimensions, I get 318 dimensions, which is a lot. Okay, so if you want to do an integral on a grid, if your wave function is too complicated and you just place 10 points per dimension, you end up with 10 to the 318 points where you need to evaluate whatever it is, your quantity you're integrating, and that's clearly not possible. And therefore, what we're going to do, we're going to use Monte Carlo to actually get configuration where the wave function square, we're going to see in a second, is more, let's say, is largest, okay? And that's a very powerful trick, and it gives us indeed all the freedom in the choice of the wave function. So this is just a summary. So here we're having an integral, a probability density, local quantity. We estimated along the path, and the question is, does it always work, and how efficient is this, okay? And to answer this, I will just remind you about the central limit theorem. So let's assume we are having a probability density P, that's our wave function squared, normalized, and the function f, and let's assume we're having the f has a finite mean and a finite variance, okay? That's the fluctuation of f with respect to m, okay, weighted by the probability density. Now, if we are able to sample m independent random variables from P of x, and we defined, the estimate, of mu as the average, as we've done before. So the central limit theorem tells you that as m increases, f of m will be distributed normally, okay, according to this Gaussian, and the mean of the Gaussian is indeed mu, so is your target whatever energy or target integral, and the variance of your average of your estimator will go like the variance of the sigma square of the fluctuations, so the fluctuations of the local quantity, divided by the total number of Monte Carlo samples. And this is irrespective of the original probability density function P of x. Okay, and so this tells us that, for a sufficient number of m, we reach the mean, and also gives us a way to estimate the error. Okay, because if I know how my local quantity fluctuates, I know that I can estimate the error on f of m as sigma divided the square root of m. So now, having this, can we just do variation of Monte Carlo, which is, as I said, sampling the wave function squared? Okay, well, you can do so if you're having something you can put on your computer, a wave function you can actually compute, as long as it's continuous, normalizable, of course. And if you're doing a chemical system, you might want to have a proper symmetry, okay, of your spin symmetry or spatial symmetry. And then, based on what we have just seen, a great desire is to have a finite variance. So if we are computing the energy, for instance, you would like that the fluctuation of the local energy are finite, since your Monte Carlo error, as I said, will go like sigma divided by the square root of m. A very nice aspect of variation of Monte Carlo is the so-called zero variance principle. Okay, so if psi approaches an eigenstate, the local energy, which is the Hamiltonian acting on the wave function divided by the wave function, will become constant, will become equal to the eigenvalue, okay? And therefore, EL of R will not fluctuate, okay? Because I have EL of R, which is the eigenvalue. Here I will have the average, which is again the eigenvalue. And in the limit of a perfect wave function, which of course we don't have, we are having that the local energy does not fluctuate. So if I do a Monte Carlo run, I do one step, I compute EL of R, and I'm done. I have the actual energy. And this is very good. So it means that also if we invest in building a good wave function, not only I will have a good let's say expectation value over whatever observable you're interested in, but if the corresponding fluctuation, go to zero, and that's automatically true for an operator which commutes with the Hamiltonian, you're going to have essentially that you will need fewer and fewer samples to get a small error bar. Okay. So this is how a typical variation of Monte Carlo run looks. So this is on the x-axis is the Monte Carlo step, So here, we are drawing a lot of samples, and the blue line denotes, the cumulative average. Okay, the cumulative average, and these are actually the local energy. You can see they're actually fluctuating a lot. This is acetone, and the scale is quite large. Okay, so it means that your sigma, so your wave function is such that the fluctuation of the local energy are of this size. Okay, and most of the local energy you're sampling will be within a few standard deviations, some standard deviation. Depends on the quality of your wave function, of course. The better your wave function, the smaller sigma, the smaller will be this distribution. Okay, but as you can see, both the energy and the LUMI square fluctuation are computed in Monte Carlo Run, and your energy will always come with an error bar. Okay, so you got to get used. It's not like density functional theory or quantum chemistry. You have an estimate of a quantity, and you have a corresponding error bar. Okay. In Variation of Monte Carlo, therefore, you have a sort of to-do list at the moment. First of all, we keep talking about sampling this distribution function P of R, which is the wave function square divided by its norm. Okay, which means to obtain a set of configuration in 3n dimension, which are distributed according to P of R. Okay, and as I said, we're going to do using the Metropolis algorithm. Of course, someone has to give you P of R, psi of R. Okay, so we need to build the wave function, and we need to choose a functional form. And a lot of research in our field actually goes in building this wave function, okay, and also optimizing it. And ultimately, you want to compute an expectation value, and you would like to have reduced fluctuations, okay? So, and of course, for like the Hamiltonian, a good wave function will give you reduced fluctuation. For other operators, this is how to do so is an open topic of research. So we start from the first point. So the first point is how do we sample our probability density P of R, so the wave function squared, and we do so by generating a Markov chain. Okay, so R is in 3n dimension, and we are moving around, going from R to R prime to R second, and we do so, so we start from an initial to a final configuration via a transition probability. Okay, so you go from Ri to F according to M. Okay, so M will be greater or equal than 0, and then the transition probability will integrate to 1 if I integrate over all the finite points. So it means if I am somewhere and I'm trying to jump somewhere else, I will not, the walker, so this configuration will not die. Okay, so I will either maybe remain where I am, or I will actually try to jump. Okay, and but actually, all we want is that if you start from an arbitrary distribution, so you don't know how to sample at the beginning, you place down your sample in a random manner, you eventually, by applying M, so by moving your configuration in space, you actually evolve to P. Okay, and to do so, we do so by imposing the stationarity condition. Okay, the stationary condition says the following. Okay, so you have P of R. And now I apply M to go to a final value, and I integrate over all possible initial configurations. So I take, my P, I apply M, and I end up in P at the final configuration. Okay, so this tells us the following. So if I have a distribution of point which is already distributed like P, by applying M, I will not mess up my distribution, but I will continue to sample P. The stationarity condition plus the fact that M is stochastic, so is greater or equal than 0 and integrates to 1, plus the ergodicity, will actually ensure that any initial distribution will evolve to P. Okay, so I'm not going to prove you this, but not only, let's say, if I have P, I keep sampling P, but also if I start from something which is not, what we desire, we will evolve to P. So my distribution of point eventually will be distributed according to P. Now, in practice, what we do, we impose a more stringent condition. So we impose the so-called detail balance. Okay, so this is my initial, this is my final configuration. We are having, and what we are doing is we want to build this M in such a way that the stationary condition is satisfied, but we actually impose detail balance. So we say if I start from I and I go from I to F, the flux will be the same, the starting from F and going from F to I. Okay, so that's a sufficient but not necessary condition. Indeed, so if I use this condition and I try to see whether the stationarity condition is satisfied, I just, write down what the stationary condition is. I take P in the initial configuration, I integrate over the initial, and I want to get P over F. By plugging in this detailed balance, so you're essentially substituting this term, you're swapping F and I, and you're using the M is stochastic, you're going to end up having P over F. So imposing detailed balance ensures you that you have a stationary condition satisfied, and if using also the M is stochastic, and therefore even if I start from the wrong distribution, I'm going to end up there. So now in practice, still we don't know how to build them. Okay, so fine, so now I have detailed balance. It's a simpler condition, but in practice I must still build it, and the way to do it is to write M as the product of a proposal matrix. So it's something that I know how to sample, which brings me from I to F, and then I decide, so I move my configuration, and then I decide whether to accept it or not. It could be that I say no, it's not accepted, or yes, it's accepted, okay? And I need to choose the acceptance in such a way that its product satisfies detailed balance. So we write down the detailed balance condition. So this is M. We factorize M in an acceptance and a transition. We do so on the left-hand side and the right-hand side. And you end up, on a condition, with a condition on the ratio of the acceptances. Okay, which is the ratio of the probability distribution, and also multiplied by the T from F to I divided from I to F. Now there are various possible choices of acceptance, and the original choice of metropolis is the one that for a given proposal transition matrix gives me the highest acceptance, okay? And the idea is that you're taking the minimum, so this ratio can be greater or less than 1. You're taking the minimum between 1 and this ratio, and so you move according to T, you compute the ratio, and then you take the minimum and you draw a random number to decide whether you're going to accept or reject the move. Okay. Now, a nice aspect of this acceptance is that in the acceptance you're having essentially the ratio of P. Okay, and that's very nice because if you're having the wave function squared divided by the norm is an integral. So we go in an infinite loop. How do we compute that integral? Especially if the wave function is something complicated depending on interelectronic coordinates. Okay, so but if you have a ratio, that cancels out. So I don't need to know the normalization to actually perform metropolis. Okay, and that's very nice because we don't know the normalization. Okay, so we can just take P of R to P our wave function square, which we can, of course, compute. Okay, you can think about a Cone-Sham determinant, for instance, or a Hartree-Fock determinant, and you may add terms to make it more complicated. Okay, in the original metropolis method, the transition is something you choose, and was chosen to be very simple, meaning it was chosen to be something symmetric. Okay, so suppose I'm in the initial position I, and I move I by drawing by sampling, let's say, a random number in a uniform box around I. Okay, the transition probability will be 1 divided by the volume of the box, okay, which is a delta to the 3a, okay? And of course, now I move in RF, and again, I draw a box around RF, which will also contain Ri, and the probability to go back, the transition, will still be 1 over the volume. And so the T will actually cancel. And you can see that the acceptance becomes something quite intuitive, okay? It's the minimum between 1 and P at the final point divided by the initial point. So if I am going somewhere where my wave function square is larger, I will accept the move. If I'm moving somewhere where this ratio is 10 to the minus 5, I'm likely to reject the move. Okay, if it is 0.3, I might, okay, it's not so bad. I might accept, I might reject. Okay, so at least we can see what this actually means. Okay, now having rewritten the matrix M, which allow us to actually perform the random walk in terms of a transition proposal matrix, okay, and an acceptance, we are having that the sequential points are actually correlated, okay? So because you're moving from 1 to F, but maybe your move is rejected and then you're staying in where you are, okay? And so your effective number of samples, independent sample is less. It may take you a bit of time to get out of a certain region, okay? And we call, if you, it's not quite precise definition, but we can define the autocorrelation time for a given observable, like, how long it takes to actually, decorrelate, okay? And your effective, number of independent samples will be the total number of samples divided by this correlation time. Okay, and what you want, of course, you want to move in space as fast as possible, and you would like to reduce, the correlation time. Okay, so and it's clear that if you're taking your box, if your box is too small, you're going to accept all your move because you're moving very, very slowly. Your wave function square will change, very, very slowly, but on your hand, you're going to move very, very slowly, and your correlation time will be large. On your hand, also the other limit is you choose a box which is very, very large. Fine, you propose huge moves, but then they are rejected, and still you're staying there, okay? And therefore, also in that case, your autocorrelation time will be large. And in between, there is a size of your box which will be optimal to move into space for the given observable you're actually sampling, okay? But, you're not forced to use a box, okay? So you can choose whatever you want as long as you can sample it. And for sure, we can sample a Gaussian, okay? And we're going to see that, for example, you can also put in your transition proposal matrix the information you're having on your trial wave function. Okay, so suppose you start from an initial configuration and you're using the gradient of psi divided by psi. Okay, so this one will actually point you to where the wave function is large. So you're better off not just sampling a Gaussian, but first, drifting and then, sampling a Gaussian. Okay, and this will be might be for your problem, a much better solution than actually just doing, something in a box. And we're going to get back to this particular form when we discuss diffusion Monte Carlo. So as I said, so we take an observable, energy is the simplest. So we sandwich Hamiltonian, we rewrite this integral as a probability density times a local quantity. We use metropolis to obtain m samples distributing according to P of R. And then we can estimate the energy, also the variance, the fluctuation or the variance if it is squared. So they're both two integrals, and you just sample these points, and you sum the quantity, the local quantity. So either the local energy or the local energy minus the average energy squared, and you have an estimate about EV and sigma. Okay, here there shouldn't be any -1. Sorry about that. I will correct it. So now, as regards computing the error, we will see in the hands-on that we are having a bit of a problem because, these samples are correlated. So you can compute an average very easily, but computing an error bar, you cannot just, treat your samples as independent. And what we'll do something which is called blocking, okay? So for the average, you can use them all, whether they are correlated or not correlated, okay, as long as you have enough, okay, to have a reasonable estimate of your variable. But when you compute the error, we will block our data along the Monte Carlo Run. Okay, and we will treat the block, so the block is a certain number of steps, okay, Monte Carlo steps, and we'll treat the blocks as our independent data, okay? And of course, the length of the block has to be sufficient, that different blocks are being decorrelated, okay? And we get back to it in the hands-on session, okay? Now, all of this work was to actually have, as we said, freedom in the choice of the wave function. Okay, so what we want a more compact representation than what is used in quantum chemistry. Okay, so in standard quantum chemistry, meaning, we would like to go beyond the use, for instance, of a configuration interaction wave function. Okay, so you can think that you are solving your Hartree-Fock problem or your DFT problem, and you build your first determinant. Okay, but then you're also having a lot of virtual orbitals, and you can start to actually build other determinants by exciting, electrons from the occupied to the virtual orbitals. Okay, and that's actually a many body representation of your wave function, and but is a slowly converging representation, because you are actually representing something which is interacting in terms of a non-interacting basis, meaning these are a lot of Slater determinants, okay, over different choices of orbitals. I excite 1 electron, 2 electrons, up to n electrons, and I very quickly end with an unmanageable, that's exponential growth, an unmanageable series of determinants. And we would like to use fewer, okay, and we're going to try to see what fewer really means. So now in the literature, people typically use what we call just-Slater wave function. Okay, so you still have a representation in terms of a summation over Slater determinants. Okay, this is what I was talking about. You're having, one, your Kohn-Sham, your Hartree-Fock, and then you start, to excite, your electron out of the first determinant. But then in front, we are putting a so-called Jastrow correlation function. Okay, and this one depends explicitly on the electron-electron distances. Okay, so Rij. So the hope is that by the presence of this function, depending on Rij, we will compactify the actual expansion in terms of the determinant. And we might get by with few, and few may still mean thousands, but not millions of determinants. Now, let's see what the Jastrow factor does, okay? The Jastrow factor, you can think, one of the first things it does is to take care of the divergences in the potential, okay? So if you're taking, an electron going on a nucleus, or an electron, ending up, close to another electron, you will have that the potential diverges. Now, your local energy, therefore, will have a potential which is diverging, and you surely, in the limit of the exact wave function, would like to have an eigenstate, but at least, for an approximate wave function, you would like it to be finite. Okay, which means that if your potential diverges to plus infinity, okay, like in the electron-electron interaction, your kinetic energy should have diverged to minus infinity, in the same way to cancel this divergence. Okay. And that's very easy to impose if you're having a Jastrow factor. So what we do is we impose so-called Kato's CAS condition. Okay, so in the case of antiparallel electrons, if the wave function is different than 0, you are imposing that the gradient of the wave function at the point where two electrons get close to each other, get on top of each other, is actually finite, okay? And so you're imposing essentially your Jastrow factor has such a form, okay? So, and it's very easy to do, to impose this conditional derivative by, for instance, writing the Jastrow factor as the exponential of a function depending on Rij. So it's going to be linear, you're going to have a linear term. Okay, and by choosing B naught to be a half for antiparallel electron and a quarter for parallel electron, you will impose Kato's CAS condition, and you will have that the local energy as two electrons approach each other will remain finite. Okay, so if the Jastrow factor looks, schematically, says pictorially, something like that, you're imposing the CAS condition, and at the same time, this is a very short range effect. You're also, pushing your electron far apart. Okay, which is not, given the shape of the potential, is quite a reasonable thing to do. Okay, so if you wonder what this Kato CAS condition are, you can think about the electron nucleus. Okay, so, and when you solve the hydrogen atom, that, the solution is Slater. They are not Gaussian, even though we always use Gaussian, they're not Gaussian, they're Slater. And indeed, they have a finite, they have a cusp, okay? They have a finite, let's say, derivative at the origin, okay? So as I said, for the effect of the Jastrow factor, you can, is pictorially imagine it, but you can also really look, this was done a long time ago by Matthew Fuchs and collaborators, look at the pair correlation function for antiparallel electrons in a particular plane of bulk silicon. Okay, so that's the probability of finding an electron given R, an electron being in R. Okay, so in R prime with one electron in R. Okay, so one electron is placed at the middle of the bond, and you can see indeed, this kind of depletion of electrons which are having, and that's actually something which the Jastrow is actually trying to mimic. Okay. Now, so the question is, should such a wave function work? So why? Okay, so what we are having is we are aiming, of course, for the full wave function, which we don't know, and what we are writing it as a factorized wave function. So we write it as a product of a Jastrow correlation factor times something else. Okay, let's assume so something else. Now this one, what we have a full wave function, a full Hamiltonian, and this is actually the equation we are trying to solve. So psi equal to psi. Now, if I factorize Jastrow times everything else, I end up with an effective Hamiltonian. So I write this equation as the Hamiltonian acting on the Jastrow phi equal to E j phi. So if I divide by j, I can view this as a very non-local Hamiltonian. So I can view Hj over J as an effective Hamiltonian acting on phi, okay? And since, J, for instance, cures the divergences in the potential, I can think that this effective Hamiltonian is actually weaker than the original Hamiltonian, the original bare Hamiltonian. And therefore, the hope is that a non-interacting wave function, or maybe few determinants, as I said, so phi will be a not unreasonable approximation for whatever else is left in the wave function. And that's the reason why, and this is, let's say, the reasoning behind such a factorized, choice, in such a factorized choice. So, of course, you're saying, okay, great. So I have, I do a Hartree-Fock calculation or a DFT calculation. I place my Jastrow. I parameterize it somehow. We have something very simple I showed you before. Here, this would be a very, very, very simple wave Jastrow factor, and then okay, my wave will have some values for my expectation value, and of course they might be good or might be bad, and that will depend on the wave function I put in. Okay, and so what you would like to actually project a better approximation than the one you started from. Okay, and to this aim, I will introduce, but I will cover it. I will just explain the concept, and then I will cover it next time. Okay, we will introduce so-called projection Monte Carlo method. Okay, so let me show you what we mean. So why do you want to go beyond VNC? Okay, so here are again all calculations. So this is a three-dimensional electron gas at a certain density, and we are plotting the energy computed for different wave function as a function of the variance of the of the variance corresponding to that wave function. Okay, so we start from a Jastrow later. We do, we have a Jastrow factor, maybe we optimize a few parameters, and then we compute, the energy, and we are up here, okay, with a certain variance. Then you say, okay, fine, my Jastrow factor was too simple. I try to put in three-body correlation, so three-body electron correlation, and of course, my energy will go down. I'm looking at a ground state, will happily go down. I have a better wave function. I optimize everything again. I go down here. My variance is reduced. And then I can actually play more. I can say, well, I start instead from here and I do so-called backflow, meaning I put a dependence on array J inside the determinant. And I automatically, I really gain a lot in energy and in variance. variance. Okay, then I can say, fine, I combine everything. I improve my Jastrow factor by putting the 3 body. I place Rij also inside the determinant, and I start to gain length. Okay, and of course you can try to extrapolate. Here I have very few points. We can do Clausius separating real line and to 0 variance. But then what you can do, you can say, okay, fine, now I use a projection method. I use this wave function, and I try to project in a stochastic manner a better solution, a better approximate solution of the Schrödinger equation, starting from my initial wave function. If I start from here, I will end up at this value of the energy, so significantly lower. Okay, so from this V and C, I go down here. Okay, and if I start, from this better wave function, I will actually end up even on the intercept of this line. Okay, so I gain even more. Okay, so what I'm showing here is that, of course, as we expect, the variation of Monte Carlo results depends on the quality of your wave function, and going beyond, we still have a bias from the initial wave function. So by using diffusion Monte Carlo, that's a particular projection method, but the bias will be significantly reduced. Okay, so now I wanted to answer. Now I forgot the question because I can have one of them open in front of me. But
I can read out.
There was a question. There was one question. I think one question I know. It was where was it? Yeah, maybe it was here. I don't know. Remember? No, sorry, guys. I go back and forth until when I find. Yes, here it is. There's somebody very, 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 very nicely picked up. Okay, so and Anthony already answered, but for everybody, okay, so somebody noticed that here there is a square root of m, but there is no dependence on the number of dimensions, meaning whether we do an integral in 3 of 100, this is still square root of m, and that's indeed one of the advantages. Of course, somewhere the dimension must come in. Okay, and of course, sigma, the fluctuation, will be sigma squared will be proportional to the size of the system. Okay, so indeed, but let's say here downstairs, so the square root of m is just square root of m. There is no additional factor. So that was one question. Then there was a question whether we move psi and we move the electrons. So yes, what you do is let me go to the last. Let me go here. Okay, so what you do is you start from a wave function. Okay, so you have your Cauchy determinant, you plug a Jastrow factor, you guess, maybe you put lots of zeros for your parameter, you guess a few, you put the cast condition, maybe some scaling that you guess, and then what you do is you sample your energy with that. Okay, so you move your configuration to compute this integral. You might compute the energy, you might compute also the gradients of the energy. Okay, and this is, for instance, with respect to the parameters. And that's a way that you say, okay, fine, now I use the gradient, an estimate of the Hessian, for instance, with respect to the parameter, and now I determine a new set of parameters, a new wave function, and then you go back, you say, now I have a new wave function. I start a new Monte Carlo Run, okay? A new Monte Carlo Run, and then I move all my configuration, I sample psi square, I get a new estimate of the energy, which hopefully is lower than the previous one, okay? New estimate of the gradient with respect to the parameter or the Hessian, I move my parameters, and then I go on. So what you do a series of Monte Carlo Run if you're optimizing a wave function to obtain, the best wave function, and at the same time an estimate of the energy or density or dipole, whatever you wish, on the given wave function. Okay, I hope that this is clear. So no, so somebody asked, is there an initial time we need to throw away? Yeah, for sure. As I said, also the samples are not independent. Okay, so it will take you, if you put down your electron in some crazy part of space, it will take you a little bit to actually decorrelate from where you started. Okay, and that's indeed. Let's say, related to the autocorrelation time. Okay, so you would throw away in the I'm sorry, I don't remember anymore where it is, the plot. The plot is before. Let me get that here. You will for sure throw away, the first few. You can see there is a hole here. We throw away the first, whatever, I don't know, 20, 30, 40 steps, so something like that. Okay, so you throw away, if you have an autocorrelation time of 2, you might throw away, 20 steps, and then you can start to accumulate. Okay, and then that's it. I think that's where we were. Okay, so what we said is why going beyond VNC? So you start from a wave function, you do your best you can, for example, to optimize the parameter, but still, what goes in comes out. And, we would like to remove the wave function bias. And I talked about projection Monte Carlo. I showed some diffusion Monte Carlo results. It's not the only choice of projection you can do, but okay, that's the most common one. And the idea is that, you're having a starting approximate wave function, and what you would like is to apply an operator which inverts the spectrum of the Hamiltonian. So something which kills the excited states faster than the ground state. Okay, so for example, diffusion Monte Carlo, your choice is an exponential minus tau h, and then there is a shift. You're going to get to the shift in a second. Okay, but the point is a minus tau h will actually invert the spectrum of the Hamiltonian. So now, of course, if I apply a projection, I need to do so in a stochastic manner, okay? And that's where the Monte Carlo comes back in. So let me see a bit what we mean, okay? So so in diffusion Monte Carlo, what you do is you say, okay, so I have a wave function, and I apply this operator, okay? I apply it once, I go from 0 to 1, from 1 to 2, and I keep applying it. Now, let's assume mathematically, of course, that's not, you don't know this, so you expand the wave function. Let's assume you expand your initial wave function on some eigenstates, which we called psi I, the eigenstates of the Hamiltonian with the energy EI. Okay, now I start from psi 0. I apply this operator n times. Okay, the 1, 2, 3 n times. So I can collect it in this manner. And now if I write psi naught as a summation of the eigenstates times the component along the eigenstates of the original wave function, the operator will become the function of the eigenvalues. Okay, so I have a sum here over the eigenstates. The operator goes through the sum, hits every eigenstate, and it becomes the function of the eigenvalue. Okay, so it becomes the function of the eigenvalue, and therefore what you can see that in the limit is an exponential, and energy which are higher than the ground state will die faster than the ground state. Okay, so as n goes to infinity, I will have that this operation will leave me with psi naught. Whatever is you still have to choose something initially which is not orthogonal to the state you're interested in. For instance, by symmetry, okay? So if you're interested in a singlet, whatever, A1, you better not choose a singlet B1 or something, So so we are assuming that this is different than 0, and you're having, this exponential, and if you are adjusting your reference energy to be equal to E naught, okay, you can estimate it as you go, so if f is reasonably close to E naught, you're obtaining in the limit of n that goes to infinity, psi of n becomes psi naught. Okay, so that's a way, that is why it's called projection. Okay, so you start from a wave function, you apply this operator, and you end up mathematically, at least, on the ground state. Okay, so now again we are in real space QNC. And you can do so in different bases. I get back to it, probably tomorrow. But what we do is, in real space QNC, we rewrite the projection equation in integral form. Okay, we are having a wave function here in R. So, and we go from R to R prime. We are having the wave function in R prime. Here we have applied the operator once. So we go from T to T plus tau. And G is nothing else than the operator, so this exponential operator, which we use in diffusion Monte Carlo, sandwiched between R and R prime. Okay, and you say, well, look at that. I go from psi to R prime. I have an integral. That's a bit like, a transition. Okay, so, and therefore, let's say maybe I could actually sample phase by Monte Carlo means, okay? And to do so, you need to, first of all, be able to sample the wave function. And we have a tiny problem that the fermions, for fermions is antisymmetric. But for the moment, we assume we are dealing with bosons. Okay, so the wave function is positive, and we get back to it again tomorrow to the fermionic situation. And now the question is, can we interpret G from R to R prime as a transition probability? And if so, okay, for the moment we do bosons. If you have also the second question answered with a yes, we can perform this integral by Monte Carlo integration. Okay. Now, to answer this question, let me look a bit, what the properties are of what we do about this green function. Okay, so what we are doing is we are having a wave function to start from, what you worked on in variation of Monte Carlo. You apply this operator, and you will have this new representation of the wave function at times t. Okay, and now you can clearly see that if we do something like that, psi at times t satisfies the imaginary time Schrödinger equation. Okay, you just differentiate, you're going to get h minus Rf down, okay, and you will have a minus sign instead of having your I, okay, your imaginary. We're working in atomic units, all h bar are gone, okay. And as I said, what we do, we rewrote it instead, not like a differential equation, but like an integral equation. Okay, so the green function is also, which is the sandwich of the operator between R and R prime, brings us from R naught to R. Okay, evolves us in space. Okay, and now if the wave function satisfies this equation, the green function also satisfies the imaginary time Schrödinger equation. Okay, with the additional condition of having a delta function at t equal to 0. Okay. So you can just, plug it in, and you can find, that that equation is satisfied because psi 0 is, in so far arbitrary. Okay. Now, so we are having an equation for G of R, and therefore we would like to actually have some approximate expression for G of R. Well, we would like to have the exact expression, but that's not possible. Something which will give us an estimate of G of R, of the G, the green function, okay? So now we can do so by looking at the effect of the Hamiltonian in steps, okay? The first thing we can do is we can say we throw away the potential, okay? So the Hamiltonian is only the kinetic energy. Now, if we write, therefore, this equation, we will have that the green function, if you have no potential, just satisfies a diffusion equation. Okay, so you have a Laplacian here, there's a minus, but there's a minus also here. That's a diffusion equation, and if you can convince easily yourself by taking the Laplacian of this function that the solution is a Gaussian. Okay, and you say, oh, great, that's a Gaussian, it's positive. Surely I can grow from R to R prime by sampling a Gaussian. So I'm doing well, okay? Then you can say, okay, very good. Now let's look at the other part of the Hamiltonian. We throw away the kinetic energy, we keep the potential, and the equation becomes something like that. And you say, okay, well, there is minus in dt. This is something, multiplying the G is multiplying the G. We are assuming is a local potential for the moment. And what you're having is that your solution is just exponential. You will have your delta function to give you the proper condition. Okay, and this is again positive. Okay, the problem is it does not preserve the normalization, but you say, okay, it's still a factor which we multiply the distribution function. I can still, imagine a diffusion where, let's say, this factor tells me, how let's say, where I'm going is a good position for my walker or for my new position or not. Okay, so let's see how we do. Okay, so now what we say is we put back things together. So we have kinetic and potential, and so we combine the previous results. Okay, so the green function we write is a product of a Gaussian, so the diffusion process, multiplied by this exponential. Okay, this branching factor. And this one will tell us whether, what are our probability of surviving or maybe dying. So is this, very small? Is this very, very large? So maybe I create a lot of children, okay? So I clone, maybe I just remain one and only, or maybe whatever, so that determines that, that I'm going to die, okay? And so now the reason why we can write it as a product is thanks to Trotter theorem. Okay, so we could do this in a bit of a more formal manner and see that the exponential of the sum can be written as the product up to some power of tau. Okay, so by writing something like that, we are writing a Green's function in the short time approximation, okay, to some order in tau, order tau squared. So which means you are choosing tau, so you're choosing a certain width of your Gaussian, you evolve, okay? But then you will have to repeat your calculation using different values of tau. Okay. So now here is a very simple situation. We're having an harmonic oscillator, and we are having essentially put down our points as a one dimension, put down our samples in a very non-appropriate manner. So we've chosen some sort of uniform distribution over this segment, okay? And we know that this is psi 0. And then what you're going to do, you're going to start to drift, to diffuse, I'm sorry. You're going to start to diffuse, according to this. And then, this one, you will compute this factor. And if V is much higher than your reference energy, okay, you will tend to have a small number. If you are lower, you will have a larger number. And so, you will end up, something like that is likely to end up dying. Okay, so for instance, this guy is dying. This one in the middle, for instance, is cloning in 2, depending on the value of the additional factor. Okay, so you are diffusing your walker, and then you decide, to proliferate and die based on the exponential factor. And, for such a simple for such a simple Green function, I'm going to see later a better way of doing things. The potential being higher or lower than the reference determines, what's going to happen to your configuration. Okay, so it means therefore that you're not going to just use one configuration. You throw down a lot of them, and then you're going to evolve them, according to such an algorithm, and maybe a bit modified, as I will explain tomorrow. Okay, but also, as I said before, you need to do a time step extrapolation. Okay, so you can see that this is taken from some paper. Okay, doesn't really matter. So you don't just do usually one calculation, but you actually do, let's say, a series of calculations, and you extrapolate. And often, let's say, if you, for the computer excitation energy, you have that the individual energy might have will depend on the time step, but maybe you're actually converging the energy difference much faster. Okay, so sometimes after you have some feeling for your system, you might just do one single time step and compute an energy difference for this. It depends very much on the quantity you're interested in, and on how we're going to get later on how you actually further modify the Green function. Okay, let us say. So now for this algorithm, you can see that you're having some problems. Okay, and then I'm going to stop here, otherwise I go too much. So this algorithm is very inefficient and very unstable. Okay, and the problem is that, as we discussed before, the potential can vary a lot. Okay, and can also be unbounded. Okay, so it can go to plus infinity to minus infinity, electron nucleus. And so you will end up either, killing your walkers, or, you might actually end up even worse, with a population which is exploding, next to the electron nucleus, if you have an electron, if you're getting close to a nucleus. Moreover, the branching factor grows, so is the potential is extensive, grows with the system size. Okay, and so also this will be something, so also this fluctuation will grow, will be something quite problematic. Okay, so we don't actually use such a simple algorithm, and how we modify, though, I would prefer to stop here. So I could go on, but I think it's better that we actually start working, and then, after you have a bit of an experience what it means to set up, to do a variation of Monte Carlo, I will move on further with diffusion Monte Carlo. Okay, so Anthony, are you there?
So everything that we're going to do in the hands-on sessions has been prepared on a website. So the address of the website is this one, and it's also in the HackMD. Okay, so you can just click on the HackMD to arrive here. So so here this link is broken, as you have noticed. So Claudia will very soon update her PDF and put it here. This will be the PDF of the second part. So next Monday and Tuesday. So for the hands-on sessions, what we are going to do, first we are going to show you how to use the LUMI machine. So we have prepared some job scripts. So so to do the quantum Monte Carlo calculations, you will need a wave function, and so we will use quantum package to generate the trial wave functions for QMC calculations. So there will be first an introduction to quantum package, and then a little introduction to CHAMP, the QMC code. And once you know what these programs are, you will be able to start to play with it. So in the first exercise, we will do ground state QMC calculations, so that you're familiar using the two codes and exchanging information between them. And then, if we have time at the end, next week, we will do the calculations on excited states. So also, it's important to see that on this web page, here on the top right, you have previous and next, if you want to navigate between the different sections. Job scripts. So we are all in this project here on the LUMI machine, and so we have prepared we have well, you need to prepare your environment with environment variables, especially for a quantum package. And so everything we have put everything inside this this file. So when you log in on the machine, you need to source this file. And basically, this file, what does it contain? It says that we want to use the Cray Python module, and also we source everything for using quantum package. So on LUMI, we're working with the Slurm batch queuing system. So you will need to use the sbatch command to submit submit your job script. And so if you want to know more about how to use this, so you can look at the documentation of LUMI, or you can search for Slurm on the web, and you will get lots of information about how to use the Slurm queuing system. So so here you can copy paste this. This will be an example of script to run quantum package. So we will refer in the next sections to this file here. And here you have examples for CHAMP below. So the two programs have different ways to handle parallelism. So quantum package is OpenMP. So basically you will reserve one node with only one task. And your task will use, let's say, 128 cores, because on LUMI, the nodes that you can access have two processors, each with 64 cores. So you can basically use 128 cores with shared memory on each node. So that's the way we're going to run quantum package. And CHAMP, so the QMC code, it's using MPI. So it's going to run 128 processes. And so you need here to specify n tasks equals 128. So you see for CHAMP, n tasks is 128. And for quantum package, it's 1. And then you have the CPUs per task 128. So it's important. Okay, basically that's all we need to say about this section. So okay, so let's go back. So now let me try to introduce you to what quantum package is. So so here you have a link to the quantum package website here, if you want to know more. But in a few words, it's a code which is not intended really for users and doing production for many people. It's just a programming environment so that you can develop new methods easily. So of course you can use quantum package to do calculations, but its initial goal was really to help researchers to develop new methods. So it's very easy to program and to play with matrix elements and things like that. So at the beginning we developed it to implement some selected configuration interaction methods. So that's what I'm going to talk about on Monday. But of course, you can do all the standard methods like Hartree-Fock, DFT, and MP2 and things like that. So here, what we're going to do today and tomorrow, we're just going to prepare Hartree-Fock wave functions for QMC and a Kohn-Sham determinant, and we're going to make a QMC run using these trial wave functions. So to run quantum package, the first thing you need to do, also if you download quantum package and you want to use it on your machine, you always need to source this quantum package.rc file that will prepare the environment for running quantum package. So as I said before, we have included this line in this file. So usually when you do some small calculations and you play a little bit, you will use it interactively, because if every time you want to make let's say a simple calculation that lasts 5 seconds, if every time you need to submit a new bash script, is going to be a bit painful. So what we recommend, just to get familiar with it, is to work with it interactively. And so to do that, you will need to make an interactive reservation on the machine. And so you can run this command, the slloc. So maybe I'm going to do it with you, so that so that you can see what is going on. So I hope it's large enough. So I log in on LUMI. So LUMI doesn't seem to, yes, there it is. Okay. So the first thing I do, yes. So I will now, yes, here I am. So I will take this slloc. Okay.
You have to run the source command first. Yeah.
No, after the slloc, because that's what I wanted to show. Yes, sorry, copy paste doesn't seem to work fine. Oh, sorry. My terminal is too big, so I'm going to make it like this because I'm not understanding what I'm writing on the terminal. It's too large. Okay. Okay, let me start again, because I think it's like this. When you do a demo live, it's always more difficult than expected. Okay. So I start again. SSH on LUMI. Yeah, maybe we have a lot of users this morning. Yeah, so this command slloc will allocate a shell. So I ask for one node using the reservation of the current training. And so that's the project number. So I ask them to have one node for 1 hour. I'm going to use only one process, and I'm asking for only 32 cores in a small partition. Because here, well, I think you could ask more because you're not very many people. So you could ask for let's say 128, like this. No, sorry. So, yeah. Okay, so this was working yesterday. Yeah, so something's weird because I tried this yesterday and it was working.
I see. I think, yeah, no, it's because of the reservation. For some reason, you cannot use the small partition. Use the default partition.
Ah, okay.
And this solves also Mikhail's problem from the chat.
Okay. So I don't know if Ravindra is with us. So Ravindra,
yeah, he is.
Okay. So Ravindra, can you please fix this thing on the GitHub while I'm...
Yes. Yeah.
Thank you. Yep. Okay, so yeah, sorry, partition is equal to default. No.
Standard, sorry.
Standard, okay. Okay, there we go. Okay, so now if you run the SQ command here, you will see everything on the machine. So you can use -u and $user, which will be your username in the shell. So I see here that I have only one job running on this compute node. It's an interactive shell. So if I run now srun with a command, let's say hostname, it will execute this command going through my reservation, and it will execute on this compute node. So normally if I run srun hostname, I should get back the name of the host. Okay, so yeah, well. Okay, so suppose everything is working fine. So I'm going to talk about quantum package now. So normally in quantum chemistry codes that you use, you always have an input file and an output file, and then you have the program in the middle, reading the input and producing the output. So with quantum package, the behavior is a bit different. You have a database where you have all your parameters inside, and you always interact with this database to change what you have inside. Let's say, for example, you create a database where you put XYZ coordinates and a basis set, so you have nothing else. And then you can tell quantum package, I want to get the Hartree-Fock energy using the data that you have in this database. So then it's going to read from the database what it needs. It's going to do the Hartree-Fock calculation, and then it's going to store everything in this database in such a way that if you ask again, give me the Hartree-Fock energy, then it's going to read the converged molecular orbitals that have been stored previously, and it's going to give it to you faster than if you start from scratch. Okay, so when you make calculations like this, you iteratively interact with this database by picking information in it and producing new information and storing it inside. Okay, so what you need to do first is to create this initial database, and so you always create it from XYZ coordinates, let's say, and a basis set. So here you will need first to, so we're going to take as an example a water molecule. So you take an XYZ file with the coordinates of a water molecule. And here so if you succeed in doing the salloc, then you need to source so salloc is going to give you a new shell. So in this new shell, you need to source this environment variables, okay? So once you're at this stage, you can run this command qp, create easyFIO, etc. So easyFIO is the name of the library used to produce the database. So it's easy Fortran input output. And so once you have sourced the quantum package environment, you have access to this qp shell function. And so you can do qp create easyFIO, and then you specify what basis set you want. So here we can use CCPVDZ, for example, and you specify the name of the XYZ file. So qp is a shell command. So you also have tab completion. Okay. So yeah, I'm going to. Okay, so I source the environment like this. And now if I type QP space and I press the tab, the tab key, I know what I can do next. Okay, so here I will create an h2o.xyz file. I put this inside, Control-C, Control-V here, put it here. Okay, so I have my h2o.xyz. So now I can do QP tab, so I can tab CR, and then with tab completion, it will automatically complete. And now, if I press tab again, I see what I can do next. So I can use the dash B like this is the same as the basis, the same as I prefer to put it explicitly. And so yeah, so if you want to know what basis sets you can use after using dash B, you can press tab again, and you see here that you have a large number of possible basis sets. Okay, so tab completion with the QP command is really your friend to help you to interact with quantum package. So that's why you don't need that much documentation, because every time it guides you in the next things that you can do. Okay, so you run this command, and now if you look at what you have here a new directory, h2o.ezfio, and if you look at what you have inside, you have subdirectories. And so if I take, let's say, AO basis, you have plenty of files which all contain the parameters. So you have the geometry, the exponents of the basis set, coefficients, etc. So you have everything that's required to understand the parameters of your wave function. Okay, yes. So next, so you can get help by using -- help. Okay, so you can read this help page, and now you can also do QP create EasyFIO -- help, and you will get now the help on the QP create EasyFIO.
Quick question, Anthony. Where is the h2o.xyz? Did we create it?
It's nowhere. It's you have to create it. You have to just to copy paste this thing.
Right.
And so I just started by creating it here, and then I just copy paste from the web, and then you get immediately this directory by running this thing, this line here. Okay, so now if you want to run a Hartree-Fock calculation, so do I still have my SLOC? Yes. So on your laptop you would do you would do this. You would do QP run SCF, okay. But on LUMI this is not going to work because it's not you're not supposed to use the login node to make computation. Okay, so and by default you don't know that the SCF is going to last for a few seconds. So here we need to use the node of that we have reserved to run the calculation. So instead of doing QP run, we do QP srun SCF and the name of the directory, and this is going to run a Hartree-Fock calculation. So you will have an output where you have some information. So you can redirect it into scf.out, for example. That's what you would do normally. And if you want to have the output both in your terminal and in the file, you can use the T command. So this is a shell. Well, it's something. It's not quantum package. It's Linux. Okay. So if you pipe a command into T will print interactively the output and will also store it in a file. Okay. So we run it like this. So now it's trying to connect to the node we have reserved. So there was something wrong with srun before. So I think there is still something wrong with srun in my shell. Yeah, it's not working as expected. Okay, so I'll try to allocate another node. Sorry about that. Very good. So I make a new reservation now. I source again the environment. Okay. Now I run this command. Okay, there it goes. So now it's yeah, I think there is something very, very strange with LUMI this morning. Well, it's supposed to last a few seconds. I don't know why it's stuck. Okay.
I can just chip in that LUMI is an amazing machine. It's the third biggest in the world, but it's a very modern architecture and there are rough edges. I mean, it doesn't maybe have to do with system being a bit sluggish right now, but
yeah, maybe well, it's good. It's going to be fixed for sure in a few. Well, I would say in a half hour it's going to work. So I'll try to do it on my computer. Okay. So just to sorry. Okay, just to be able to do something. Okay, h2.xyz. Okay, let's start again. We'll go back to this thing. So now, so on my laptop, I will do qp run scf h2.easyfio and then tscf.out. Okay. Ah, sorry, I need to. That's specific. I compiled with the Intel compiler. I didn't load it. Okay, there we go. Okay, works. So here you see you have a typical SCF calculation where you have the energy going down, etc. And now you have the Hartree-Fock energy of the water molecule. Okay, and so as I told you, everything is stored in the database. So here in the MO basis, we have stored some molecular orbitals, so that if I run again the same command, okay, you will see that it converges in one iteration because it already has molecular orbitals inside, and it tried to run the SCF using the molecular orbitals that are inside the directory. Okay, so that's just a special. Yeah.
Maybe we should slow down. So and ask, how many people, where people are, or you would just want to keep going? You think people are nowhere?
Yeah. So
this is fast.
This is fast. Okay. Okay.
Well, I don't know. Maybe it's all clear for everybody. So are people trying it on LUMI? Are they actually able to do something, or is this also stuff for them?
So I would suggest to wait a little bit before playing with LUMI, because yeah. So
can you re-go through quick?
Yeah, I think to go through quickly before. And
okay, Daniele says
people try it and play with it by themselves. Yeah, because well, I really suspect that the problem is not me, but it's LUMI, because I've been trying it for the whole week last week, and everything was.
Sorry,
was okay.
Anthony. Sorry, keep going.
Yes. Okay, so here I just show you a way to run SCF calculation, and so then you have also about quantum package. You have to interact with the database. You have this command qp edit h2.easyfio, and if you run this, what it does, it reads everything which is in the database. It produces a temporary file like this. It opens your favorite editor with this file so that you can modify it interactively, and then when you save, it puts back the values inside the database. Okay, so it's just a convenient way to edit the parameters that you have. So if I search for the Hartree-Fock section or Hartree, I have here SCFUT, so I have different control parameters of the Hartree-Fock algorithm. Okay, so this is where you can modify interactively let's say here the MO guest type was Huckel, so I could use H4, for example. So that's a convenient interactive way, but then you can also change parameters using the shell. So so if I use qp set file h2.easyfile, now I can use qp. Let's say so I can do qp set or qp get to interact with the how do you call the database. So I could see, for example, qp get Hartree-Fock energy, and then I have here in the shell the energy. I can also, if I want, qp get SCF utils, let's say SCF algorithm, and here I get DIS. And if I want to change it, I can do something like this: qp set SCF algorithm, and then I can put what's the other one? So let's take another example, because I forgot the number of iterations maximum. I can set it to 10 if I want. And now if I get the maximum number of iterations, oh, sorry, it is 10. Okay. So this is just to show you that you can use qp edit to modify the control parameters of the programs, or you can use the shell like this, such that running quantum package calculation basically is producing a large batch script where you interact with your database incrementally. Okay, so here, so that was just for running a Hartree-Fock calculation. So now, if we're going to we can run a CI calculation, a configuration interaction with single doubles. So this is very easy. So you can do qp run CISD with the name of the file. So to do that, you need, of course, molecular orbitals, because here we do the CI using Hartree-Fock orbitals. So if I run it like this, it's going to run a configuration interaction using all possible, exciting all the electrons. So you don't really want to do this. You need to specify that you want to do only a valence calculation, because that's usually what you would do. So you would do here qp set frozen core, and you see here that now it has changed the orbital classes that you have here. You have a core orbital, which is orbital 1. And you have active orbitals, which are orbital from 2 to 24, which are all the orbitals, okay? And now running qp run CISD with H2O, etc., and I put the result into CISD.out. Here you see that it runs the CI calculation, okay? And the wave function is stored inside the database. So now if I do qp edit again, if I go at the bottom of the file, I see here determinants with CI coefficients, and here representation of the determinants with the alpha spin and beta spin with the occupations from left to right. So this is the Hartree-Fock determinant. Here is a double excitation where we have excited these two electrons into this orbital, and you have the coefficient here, etc. So you can have a look at your wave function just to see what you have inside. And when we will do QMC calculations, what we will do is to export the wave function calculated with quantum package into a file that we'll call a TREX-IO file, and CHAMP will use this TREX-IO file, extract the data it needs from it, and prepare everything for CHAMP. So okay, so that was the short introduction for quantum package. So I can just tell you a few words about TREX-IO. So I haven't prepared anything here, but I will put you a link. Okay, so TREX-IO, it's a library that we are developing within the TREX Center of Excellence. So the idea is really to define a standard format for exchanging wave functions between the codes. Because for QMC calculations, it's really necessary to be able to get a wave function. And so so here you see on the website of TREX.io, you see everything that you can store inside the TREX.io file. But the idea is that you would use one code, save the data in TREX.io, and then use another code, read the data in TREX.io. So just in your mind, it should be the equivalent of what JPEG is to pictures. Okay, so we want a standard format for wave functions that everybody understands, and so that's TREX.io for us. So I think I can stop here with the presentation of quantum package. So I don't know how you want to proceed. Do you, Claudia? Do you want to present CHAMP in a few words, or
no? I think there was somebody also in the chat who was asking for a recap of what you were saying. So I would say that we first. What time is it now? Let me see, 11 or 8. I don't know. It seems to me that if we start already with CHAMP, they get lost.
Okay. So then what you could do probably is try to log in on LUMI. I hope you will be more lucky than I was, and then you can try just to run the Hartree-Fock calculation and the CISD, following everything which is on this introduction to quantum package page. It shouldn't be too difficult, and so just try this. Well, if LUMI doesn't respond, then I think I cannot do anything for you. But then if you have any questions about interacting with quantum package and etc., I'm here to answer your questions.
So Sophia asks, can you just repeat how you create the database?
So you can look at section 4 here. So you have an XYZ file on your computer, whatever file. So here, what I propose to do is to create one using these coordinates. So that's a water molecule in XYZ format. So you open a file, you copy paste this inside, and you call it h2o.xyz. Okay. So now on your computer you have nothing but just h2o.xyz, and then you run this command, and so you choose what basis set you want, and what's the XYZ file that you want to use, and this will create the directory h2o.easyfio on the machine. And so you have different options also on the QP create easyfio. If you want to change the multiplicity, the charge, or if you have coordinates in atomic units, etc. So there are some. So I can maybe probably show you. So if you QP create with help, then you have all the different options that you can use to do different things. And we will see in when we prepare wave functions for QMC calculations that we will need to use pseudo potentials, and you can also here specify that you want to use some pseudo potentials. So really, this command is the starting point of using quantum package. So there's another starting point, which is that you could convert outputs of Gaussian or games to create an easyfio database with the molecular orbitals inside, and then you can prepare. Let's say you can do a CASSCF with games, and then you can use these MOs to do whatever you want with quantum package later on. So do you have any questions? So I'll try to open the yes. Okay, let me.
If later we perform an SCF with another basis, are the old results here with CCPV DZ erased?
So you cannot change the basis. Once you have created with the basis, you have to stay with this basis. Yeah.
Yeah, but
or
what
you create another directory and then you work on another base. Yeah. Okay, so I try to answer the questions by with my voice but also you can unmute your microphone and we can try to speak if you want. So the SLOC, what it does, it really you make a reservation in the same way as you would do with SBatch. So when you reserve some nodes, so you appear in the queue. So the nodes are yours, but they're just waiting for you to use them. So once you have made this reservation with salloc, the machine will give you a new shell. And in this shell, every time you use srun with a command, it will execute the command using the resources that you have allocated. So let's say if you use salloc with, let's say, 10 compute nodes, when you will run srun with your program, then it will run the program on the 10 compute nodes. So it's a way to interactively run some parallel calculations with MPI on different nodes. Okay. But you can also use it to reserve a very tiny amount of reservation on a supercomputer. So it's pretty useful when you're doing benchmarks, because when you do benchmarks, you want to always have the same. You want to run the same code on always on the same compute node. So here you say I reserve it for the morning, let's say for 4 hours, and then I always run on the same hardware. And so every time you use srun with a command, it's going to SSH on the node. It's going to run the code on the node, and the standard output and standard error will be redirected into the shell where you were. But you're still logged in on the login node. You're not, when you do salloc, you're not on the remote node. Okay. So you have all now run quantum package. So CHAMP. So CHAMP, in a few words, is the QMC code developed in Claudia's group. So here it has been all installed by Ravindra and Claudia. Wow. And so they have also prepared at this place here a tar.gz file containing many directories. So this will help you if you are stuck in some at some examples. You will be able to see the files that you should have. Okay, so these are you could see this as a solutions.
Not all files. There will be input. I think the input, the shell script command, TREX.io. But still, some things you will have to do.
You still have to fill in some
few things. Yeah.
Blanks. Okay. Okay. So now, So now let's start to try to do some real calculations. So what we're going to do here is what you can see here. So we're going to run quantum package, then produce a TREX.io file, and then use this TREX.io file into CHAMP. So, okay. So what we will do here, we will take so is it still the water molecule? I think yes. So water molecule. So it's the same geometry as what we had before, and we will produce. So we will produce two wave functions. One Hartree-Fock determinant. And we will also produce a CONCHAMP determinant. So we'll have to do also a DFT calculation. And then we will use these two wave functions as trial wave functions for QMC calculations, so that you can see in QMC what will be the difference between two different kinds of wave functions. And so there was a question this morning about how the variance scales in QMC. So I answered in the chat that if you have let's say a Hartree-Fock wave function, so Hartree-Fock basically will always give you a similar variance, but if the system grows, the total energy will grow with the system, and so the relative error that you will make will stay similar. So the variance will grow with the energy. Okay. So if you have let's say H2 molecule, the variance will be small because the total energy will be close to 1 Hartree. But if you do a copper atom where the total energy is 1,600 atomic units, then the variance will be enormous. And when you do chemistry, you're targeting the milli-Hartree accuracy. So a milli-Hartree in a copper atom is harder to get than a milli-Hartree on H2 because of this problem of variance. So to solve, basically to solve this problem, what we do in QMC usually, we remove the core electrons and we use pseudo-potentials. So this has the effect of having the total energy that becomes much smaller in magnitude. So for the water molecule, you remember we had minus 76 atomic units. And here with pseudo potentials, you will get something more like minus 17, if I remember. So it's much smaller in magnitude, and so the variance will also become smaller by this effect. And there is another reason why we use pseudo potentials. It's that the core electrons, when they get close to the nucleus, there are a lot of fluctuations of the local energy in this region, because you can have a very large potential and also a very large kinetic energy, and so you are making the addition of the subtraction, of two large numbers to get something small. And so this is subject to very large fluctuations. So by removing the core electrons, we're able also to remove a region of space where the fluctuations of the local energy are large. And so it also has the effect of reducing the variance. So using pseudo potential has many different positive effects for QMC. So that's why we're going to use them. So, a very good choice of pseudo potentials for QMC are the Burkatski-Filippi-Dolg BFD. So there is a website here. If you click on it, you can choose different. So you can select pseudo potentials here for different atoms. So yes, so this website hasn't been updated. So the hydrogen is not the best one. And so this is why here we provide the pseudo-potential parameters for the hydrogen, which are better. And so they are here written in games format. Okay. So,
Anthony, maybe you can express the concept of a pseudo-potential for hydrogen. Because it's be surprising.
Right.
Yeah.
You're completely right. Yes. So yes, so there are multiple multiple reasons to use the pseudo potential. So this morning, I don't know, did you explain the problem about the
No, but I think it's just the only thing I wanted you to say, but that I can say was that, not to make it too complicated, is that, okay, of course we don't remove any electron, there is only one, so you cannot remove an electron like you do for carbon, where you throw away two, so you don't remove an electron. Nevertheless, you smoothen the how is it called, the divergence of the electron nucleus potential close to the origin. Okay, so this one will give you, especially we're going to use Gaussians then, and will give you also smaller time step error. So we pseudize also hydrogen, but only smoothening the divergence. That's all what we do. Okay, that's all what I think. Let's know, Anthony.
Yes. So if I can try to rephrase it, when you will compute when you will do QMC, you will compute the local energy. So at some points, so you will have your electrons at some points of the 3n dimensional space. And if you have one electron going on a nucleus, you will have the potential, which will be -1 over r. Okay. And so you have a negative divergence. And so if you want to have the energy to be finite, you need to have a divergence of the kinetic energy on the with the opposite sign, so that it really compensates and that your energy stays constant. Okay, because the energy is T plus V. And so if V diverges negatively, you need to have T to diverge positively in the same way, so that E stays finite. So the thing is that we use Gaussian basis sets usually in triangular wave functions, and with the Gaussian basis sets, there is no way that the Laplacian of the wave function will diverge. So the Laplacian will always be finite. So to make things smoother, as Claudia said, instead of trying to have the Laplacian diverge, we use a pseudo potential that doesn't diverge at the origin, so that when you make the sum of the Laplacian and the potential, both don't diverge, and so you still get a finite energy. It's another way to say the same thing as Claudia said. So there are multiple benefits. So you cure the divergence of the energy. You remove core electrons if needed. So here you would remove 2 electrons and here 0. So if needed, you can remove also electrons, and you make the magnitude of the total energy smaller. So it's a very good thing. Okay, so first what you will have to do is you create an XYZ file like this, and you create another file. So here we call it pseudo. You could call it whatever you want, but here we said let's call it pseudo. And also, when you use pseudo potentials, you cannot use any basis set. You need to use a basis set which is adapted to the fact that you have a pseudo potential. So for each pseudo potential, you have different basis sets adapted to it. And here, here we have the basis set parameters adapted to this particular pseudo potential. So in quantum package, I have shown you this morning that you can use QP create. Dash B. We were using CCPV DZ. So when you run this command, what's happening is that this command is trying to look if you have a file named CCPV DZ in the current directory. And if it's not the case, then it's going to try to look in the database of quantum package if it can find this basis set. So if you want to specify your own basis set, you create a file and you use the command, and here you put the name of the file containing the basis set. And for the pseudo potential, in the same way, you use -p, and so if I use BFD, then it's going to search in its database, in the database of quantum package for BFD pseudo potentials. But I told you that the hydrogen is wrong, so you shouldn't use the database of quantum package, but you should use instead these parameters. Okay, so I hope I was clear. Yes, so that's the command line you're supposed to run. So first you will run a Hartree-Fock calculation like this. So here I put again the salloc. So here I think that there should be probably also the problem of, okay, no, partition standard, well done. Yeah, so it's fixed. Okay, so first you run a Hartree-Fock calculation like this, and after having your Hartree-Fock wave function, you just need to run this command to set the name of the TREX-IO file that will contain the Hartree-Fock wave function that you can give to CHAMP for the next for what follows, and then you run QP-S1 export TREX-IO H2O HF. So this will read this H2O HF database and will create this file. So once you have done this, you have a single file with the Hartree-Fock wave function inside, and then we ask you to do exactly the same thing with a DFT calculation and export an H2O DFT.TREX-IO file that will contain the CONCHAM determinant. And once you're at this stage, you will be able to start doing QMC with 2 different wave functions. Okay, so that's the first part. And just also, once you have done this, you also have another, so you have seen you could do QP run SCF, QP run CISD, but we also have a program which is called print energy. What it does, it just calculates the energy of the wave function that you have in the directory. Okay, so if you have made a Hartree-Fock calculation, QP-S1 print energy will give you the energy, the Hartree-Fock energy. But then if you have a CONCHAM determinant and you ask print energy, it will give you the energy, not with the CONCHAM Hamiltonian, but it will give you the energy with the real Hamiltonian. Okay, and this is what also you will get from QMC. So when you run the DFT calculation, you will get something which is lower, like minus 17.2, let's say. But if you want really to evaluate what's the energy that I will get with a real Hamiltonian using this determinant, the variational principle tells you that it should be higher than the Hartree-Fock, because it's another determinant, and Hartree-Fock is the optimal solution. So it should be something a little bit above. Okay, so this little program allows you to tell you what the QMC calculation that you will run later on should give as an answer, just to check that everything is correct. Okay, so now I think you can start to do everything that is in 1, 2, 3, 4, and then you will be able to do the QMC runs once 1, 2, 3, 4 is okay.
Yeah, I hope everyone has reached this point. So there is a project directory where common files are kept. There you will find a tutorial champ.tar.gz, which you should copy that to your home directory. This is the folder. Let me go back to my directory. There you will see a list of example folders, which are given with some files, but you have to fill in some details there. And the first one is to take the TREX IO files, let's say H2O dft.trexio or H2O hf.trexio, and then do the QMC calculation. So let's first look at the first part.
Sorry, Ravindra, can you zoom in a little bit on the web page?
Okay. Good enough?
Yeah.
Yeah.
Mm-hmm.
Okay, so here I'll assume that you have the TREX IO file, and then you have the tar.gz, and which you have extracted. Let's go to example 01 for H2O HF calculation. So here I have the TREX IO file already, and I have given 2 submission scripts. Let's look at the submission script. So here it's the same which appears on the web page, but the path to champ is given in the submission script, and the input file name and the output file name, and the error and warnings will go in this file. So most probably you should use this file. I have given estimated time to run this calculation, and this does not take a longer time for H2O, let's say. So 10 minutes are more than enough. And we will use 1 node and 128 cores. Okay. Now, if you look at the web page, here we have the TREX IO file. So there are 2 ways in which you can run champ. You can use directly the TREX IO file without extracting its details, or you can visualize the TREX IO files by converting them into text files which are needed by the champ. So here is the conversion script which comes with champ, which is also available at this location. You can see that it was a part of TREX IO tools. This is a Python script. So if you are running this and if it doesn't work, just do module load a Python. This should make it available. The Python should be made available with this. Okay, so it has some flags. So with --TREX, it will read the TREX IO file. So within this TREX IO file, you can store the full wave function. So you have to tell which types of molecular orbitals you are going to use here. This is the backend HDF5. There is another backend for TREX IO which is text, but currently we have HDF5 file format. This is the prefix for the basis set. It's just a name. So for CHAMP, we will need LCAO. These are the orbital files to be extracted from this TREX IO file. Then the geometry, and then the basis, the pseudopotentials or ECP, and the determinant. Since this is a HF calculation, it will be just a single determinant. So if you run this, and hopefully if the file is this, if it is present in this folder, it will work. Okay, so it prints some details. It read this file. It's not a games calculation, so it's not printed here. It uses the canonical orbitals. The backend is HDFI, and we requested LCAO, geometry, basis, ECP, and the determinants file. And some of the warnings are there, but because TREX IO didn't store these details, but it's good enough. Now, if you look at the folder, you will see that there are some files created. So let's open this one, the pseudopotential file. So it has extracted the information from TREX IO file and made into a text file which is readable. Similarly, say a geometry. Yeah, so it has all the details. And if you want to visualize the TREX IO file itself, you can do this. Module load, I think HDF5. This will enable a tool. It's called H5 dump, and you should give the TREX IO file name and give some name. And this will give you the HDF5 file format for the TREX IO. So you can visualize what are the details stored inside the TREX IO file. So it has all the required information for a wave function. All right, so we have to create a pool directory here where all the basis, all the pseudopotentials, geometry, and there is one file called basis pointers, which I will explain later, will go into the pool directory. So if you go in pool directory, you'll see so here are some details like how to read the basis file. So there are 14 AOs for the first atom, 2 of which are S type, 2 of which are P type, like that. But it's a slightly detailed. You need not know this part because it's taken care of. So now your folder is ready. You can run the calculation. You should have determinant and LCAO in the same directory where your input file is. And the pool directory should have the basis, ECP, and the geometry and the basis pointer files. So if you look at the input file, here is the structure. So you can put some general, the CHAMP input file is separated into modules. So there is a general module, there is electron, VMC, DMC. So you can put this information. And here it tells what is the calculation mode, what is the basis. So this is the same keyword which we gave in the basis prefix for the TREX IO, and it's the name of the pseudopotential file which we put in the pool directory. So here load molecule will load the molecule. It will read the information from the pool directory with this file name, which is the same as what we created now. Same for basis info. And the orbitals is read from the current local directory. And there is one more jastro.start, which you should copy from the web page, which is actually no jastro file. There's no jastro parameter, but we should give this. And let's create jastro.start. Okay. Now it has all the information. So total number of electrons, total number of up electrons, and these are the VMC n step and n number of blocks. So if you look at
Ravinder, tell them what blocks and steps.
Okay. So in Monte Carlo calculation, you can have so you can do VMC calculation in one block. You can go, let's say, n number of steps. That is VMC n step, and total simulation will be for n step times number of blocks. And then but make sure that VMC n step is at least 10 times more than the correlation time, which you will see in the output file of this calculation. Yeah, and let's look at the other script which reads the TREX IO file directly. So here I have given VMC H2HF underscore TREXIO.inp, and let's open that file. Yes, so you should rename this. File name has changed. Okay, so currently it needs only this TREX IO file and the JASTRO file. Everything else will be extracted automatically by the CHAMP. Now you can sbatch, say the first one. So it's doing the calculation now. And at the end, it will print the summary and the final result.
Yeah, so the first column is the average of the local energy over the number of step 20, and the second column with the error is the cumulative average with its error, which is then printed under total E. Okay, and you can see at the end you have a T-core. I'm sorry, Ravinder, I'll let you back. A T-core which is less than 2, and we shows 20 as a step. So we are good. Our error bar is reasonably well estimated, and sigma is just the LUMI square fluctuation of the local energy. So we will put some more information maybe on the in the index on the website. Sorry.
So so you have finished this calculation. You get the VMC energy for H2OHF, and let's compare this number with the number which you got from the QP. So 169500, and this is 169503. If you want more accurate results, you should run this longer, but this current result is accurate within this error bar. And this is in Hartree. Okay, so this is the Hartree fog calculation. So similarly, you will have a DFT folder. You will have DFT TREX IO file, and the input file is prepared for you. But you have to convert this TREX IO file into the text files which are needed for the CHAMP calculation, and then you can run this script. You can just submit sbatch LUMI example 2, and then you should get this energy. I mean, close to this.
Maybe we should stop here and let them do it.
Let them do. Yeah.